solve the problems using backtracking. Okay, backtracking is where it makes use of the depth first search technique. Okay, so basically the problem will have a graph involved in that one, and we will start from one of the vertex in the graph, and then we'll try to do the depth first search in order to solve the given problem. And we will make use of the, since we are making use of the backtracking, which involves coming back to the previous vertex if there is no solution exist. Like this way we will keep on finding the set of solutions. Okay, we need to remember the concept that the backtracking gives us a set of solutions for the given problem. Today the problem what we have taken up here is that called as Hamiltonian cycle. It is called as Hamiltonian cycle. Let us see, understand what is the problem, or what is the statement of the Hamiltonian cycle is. Okay, assume that there exists a graph. Okay, say the graph GVE, a graph containing n vertices. Okay, it contains n vertices. Okay, fine. So if a graph is said to be Hamiltonian cycle, okay, only when it has to adhere to certain rules. Okay, certain rules in the sense it also will have a bounding function here. So bounding function in the Hamiltonian cycle is that, suppose I will explain this particular Hamiltonian cycle first with respect to the example, then I will take up the definition. Okay, let us say there is one particular graph here. The graph here is what? This is the graph here. Okay, the graph contains how many vertices here? It contains 5 vertices. It contains 5 vertices, and there are, all these vertices are connected, okay, through these particular edges. Okay, now Hamiltonian cycle, what it says is that we need to find out a path in this given graph such a way that if we start from one of the vertex, then if we proceed further visiting all other vertices exactly at once, and we should return back to the starting vertex, making it to be a cycle. Okay, Hamilton cycle is the graph where if we start from one of the vertex in the graph, and if we keep on visiting all other vertices exactly once, okay, such a way that after visiting the last vertex we should come back to the first vertex, then we can call such a graph as to be Hamiltonian cycle. Meaning here is that, suppose this is one of the graph here. Okay, now suppose if I start from the vertex 1, what I should do, I keep on visiting the its connected vertices. So 1 is connected to 2 and 4. What I will do is that I will travel from 1 to 2. Okay, so 1 to 2 is connected. Now 2 is connected to 5. Okay, then 5 is connected to 3 as well as 4. Now this time I will choose it to be a vertex 3, that is from 5 to 3 I will travel. Then from 3 I will travel to 4 because it is connected. Then now if you notice here, all these vertices I am visiting exactly once. I am not visiting the same vertices more than once here. Okay, so I have covered all the vertices. What is the last vertex here? Vertex number 4. So after vertex number 4, I should reach the first starting vertex. What is the starting vertex in this particular list? That is 1. So is there a edge from 4 to 1? Yes, there is an edge from 4 to 1. So from 4 I will travel to 1. So what I have done here is that I have started from one of the vertex 1, and from then 1 to 2, 2 to 5, 5 to 3, 3 to 4, and 4 to 1. So what is happened is that when I started from 1 and I continued visiting all other vertices exactly once, and after visiting the last vertex I could come back to the starting vertex. I could able to return back to the starting vertex. So this particular path, that is from 1 to 5, 3, 4, 1, is said to be a Hamiltonian cycle. So Hamiltonian cycle means if there is a graph GV containing n vertices, if I start from one of the vertex and from that particular vertex I should be able to visit all other vertices exactly once, and from the last vertex I should return back to the starting vertex, then such a graph is said to be a Hamiltonian cycle. Such a graph should said to be containing of Hamiltonian cycle. So in a particular graph, there might be one Hamiltonian cycle or there could be a set of Hamiltonian cycles. So in order to find out how many Hamiltonian cycles are exist in a given graph, we make use of the concept of backtracking. Okay, so we have seen that backtracking, in order to find the solutions to the backtracking, we try to draw the state space tree diagram. If we can draw the state space tree diagram and if we get the solutions over there with respect to the bounding function, then we can say that the solutions or the set of solutions can be achieved or can be solved for a given problem. Now here, suppose in the same graph, say if I start from what, if I say, let me try to traverse in a different manner here. Say if I start from 1, from 1 to I will go to the second vertex 2, and from 2 I will go to say 5. Okay, now here from 5 there are two edges, that is one goes to 3, one other goes to 4. So this time if I say, if I choose 4, okay, then after 4 I have two possibilities. One I can go to 3, other I can go to 1. So from 4, what is the remaining vertex here I have to go? I have to go to 3 here. So I will from 4 to 3 I will reach. See, when I look at these vertices, all the vertices I could able to reach. But from last vertex, is there a edge to 1? From 3 to 1, there is a edge? No, there is no edge. So this particular path doesn't give me a Hamiltonian cycle. So this is not a Hamiltonian cycle if I travel in this particular way. Okay, so let us try to see what are the other Hamiltonian cycles here. Now, from 1, earlier I have chosen to travel to the vertex 2. Now since 1 is also connected to 4, so from 1 I can go to 4. From 4 I have what, how many, two solutions are there, two paths are there. One is towards 5, other is towards 3. Suppose if I reach, say from 4 if I go to 5, okay, then from 5 there are two options. One I can go to 3, other I can go to 2. Okay, suppose in this case if I go to say 3, what happens? So 1, 4, 5, 3 I have visited. From 3 I have only one option to go back to 4, but 4 is already existed. I have visited 4 already. I cannot visit the same vertex not more than once. Okay, so this is again a dead end. So this is not a particular solution. So what I can do again, I can say 1, 4, 5. Okay, 1, no, not 4, 1, 1, 4. This time if I say from 4 to 3, if I go from 3 to, I can go where, 5 I can go. From 5 I can go to 2. From 2 I can go to 1. So here we may notice that I started from 1 and I visited all the vertices exactly once. And from last vertex I could come back to the starting vertex. So again this is one of the solution. If you keenly observe these two solutions here, the one which I have highlighted over here, this one and this one, both are again mirror images. We have seen this particular concept where in the Queen's problem, if we get one particular solution, then the mirror image of that would be another solution. So in this particular graph, these two are the solutions. That means these two will give us a Hamiltonian cycle in the given graph. Now let us try to solve this particular problem, Hamiltonian cycle problem, using the backtracking process, that is by drawing state space tree. Okay, so let me clear off these things here. Okay, is this particular concept understood as of now? Are there any doubts? Yes, students, any doubts here? Okay, fine. So we will start from say vertex, one particular vertex, I will mark it as 1, vertex 1 I will start. Now vertex 1 is connected to what? It is connected to 4 as well as it is connected to 2. So this time what I will do, I will choose that vertex is connected to 4 and then I will try to travel in this particular fashion. Okay, so from 1 to 2 I will join, 1 to 2 I will travel. Okay, now next 4 is connected to what? It is connected to 3 as well as 5. So this time what I will do, I will choose from 4 to 3. So I will have one more node over here. Okay, and this node is 3. From 3, 4 and 3 I will join now. So 4 and 3 I will join. So this path is existed. Okay, fine. Then I reach 3. From 3, what are the edges? 4 and 5. 4 is already traveled. Then from 3 to 5 I will go. So that particular 5 I will mention it over here. So this is 5. Okay, 5 I visit. Then let me join the edge here between 3 to 5. So 3 to 5 is connected. Now from 5, where I can go? From 5 I can go to 4, 3. But 4 and 3 are already visited. So I should not visit those two vertices once again. So where else I can go from 5? From 5 I can go to vertex number 2. So this 2 I will choose now. So here I will be visiting to 2, that is from 5 to 2. So let me draw the edge between them. So 5 to 2 I will visit. Okay, then from 2, where else I can go? 2 is connected to 5, which is already visited. Then 2 to 1 I can go. So 1 once again I will visit, and this time this 1 is what? Again the starting vertex. It is the starting vertex. We started from 1 and we could able to navigate, or we could able to visit all the vertices exactly once, and we could come back to the first vertex, that is starting from the uh, vertex number 1, 4, 3, 5, 2 and 1. So this is one of the path which could give us the solution as a Hamiltonian cycle. Okay, now suppose if we go, that is if we backtrack over here. Okay, backtracking means what? Suppose from 1 if I come back to 2. Okay, now from 2 where else I can go? There are no other edges, so I can only go back to 5. So I will come back to 5. So from 5 where else I can go? From 5 I can go back to what? 3 or a 4. So 3 or 4 both are covered, so I cannot come back. So I can go to 3 here. So 3 is connected to 4. Okay, so which is already visited, so I cannot go back. I cannot go to the fourth one, so I will come back to the, I will do the backtrack and I will come back to 4. Now from 4 there are total 3 edges. Among 3, one is coming from 1 which is already visited. Second one, what we have traveled? We have traveled to 3. Okay, that we have already taken. What is the left out? The left out one is 5. So that from 4 to 5 we can go. There is one more possibility that from 4 to 5 we can go. So this time what I will do is that from 4 I will travel to the vertex 5. Vertex 5 over here. So let me join these two edges, these two vertices. Let me join here. So 4 to 5 I can go. Now again from 5, since there are three edges, 4 is already covered over here. I can go to the 3 or I can go to 2. Okay, so now this time let me choose it to be a 3. So from 5 I can go to 3 here. I can go to 3. Okay, let me connect the edge between 5 and 3. So 5 and 3 are connected now. Okay, now from 3 where else I can go? I can go to 4. But is it allowed to go to the vertex 4 from 3? No, because this particular 4 is already visited in this particular path. So I cannot visit the 4 vertex from third vertex. So this is a dead end. So the bounding function we could not able to apply at this particular stage. So the continuation of this particular, at this stage we have to kill it. So this 3 will become a dead end over here. Okay, so from 3 what else I can do? I can come back to 5. I can backtrack to 5. So from 3 I could come back to 5 here. So from 5, where else I can go? I can go to 2. Correct. So this time I will try to see that I can go to vertex number 2. So I will reach vertex 2 from 5. Okay, so let me connect the edge between 5 and 2. Okay, I could able to connect it over here. Fine. Now from 2, 2 is connected to what? 5 and 1. From 5 is already covered, so from 2 to 1 I can go here. But what about this one? One is also already visited, which is the starting vertex. So if I connect, that is if I travel from 2 to 1, so what I'm trying to do is that I'm going to go back to the starting vertex. But have I reached or have I visited all the vertices in the given graph? If you look here, 1, 4, 5, 2, and after 2 I am coming back to 1. So I am not traveling to 3 here. That means, so this is also not a solution. So this is again a dead end over here. I cannot go back, I cannot reach 3, the vertex 3 from 2. So from 2 to 3 there is no direct edge. So that is also again a dead end. So what I can do, I can come back to 5 over here. Backtrack to 5. So all the possibilities from 5 I have validated. So now I should come back to from 4 also I have validated all the possibilities. So again I should come back to vertex 1. So from one vertex, where else I can go? That is, I can go to vertex number 2. So this time I will choose it to be a vertex number 2. Okay, so I will reach 2 from vertex 1. Okay, so let us join the edge between 1 and 2. So 1 and 2 are joined over here. So from 2, where else I can go? I can go to 5 here. So now this time I will choose it to be a vertex 5. So vertex 5 I will visit. Okay, then let me join the edge between 2 and 5. So 2 to 5 I visited. Then from 5, what are the possibilities? I can go to 4 or I can go to 3. So this time what I will do is that I will choose it to be a 5 to 4. So 5 to 4 I will try to visit here. So 5 to 4 I will go. Okay, and we'll join the edge over between vertex 5 and vertex 4. Okay, so I started from 1 to 2 to 5, then to 4, and from 4 what are the two possibilities I have? I can go to 1 or I can go to 3. So among this part, what is the left out one? Left out is the third vertex. So from 4 to 3 I will try to travel this time. So 3 I will visit. Okay, from 4 to 3 I will visit, and let us join the edge between those two. So 3 to 4 are connected now. Okay, now I have visited all the vertices exactly once. So what I should do here is that I should come back to starting vertex from the 3, that is third vertex. So is there a edge from 3 to 1? No, there is no edge. So bounding function would not able to satisfy here. That means this is again a dead end. This is not giving me a solution. So what I have to do? I have to come back, that is backtrack to the previous vertex. Since the previous vertex to 3 is 4, so 3 to 4 I can do. So from 4, where else I can do now? I can go to 1. Okay, but if I go to 1, would that be a proper solution? No, that will not be a solution, because I would not be covering all the vertices. That is 1, 2, 5, 4, 4 to 1. If I travel in this way, I would be skipping vertex number 3. So that is also a dead end. So I cannot do that one. Then what else I can do? I can again backtrack. Backtrack to what? The previous vertex, that is vertex number 5. So from vertex number 5, earlier I traveled to 4 and I did the tree. Then now I have to do what? I have to start from 5 to 3. So this time I will reach 3 over here. So I will travel to the vertex number 3. So let us join the edge between these two vertex. So 5 to 3 we will travel. Okay. Then from 3, where else I can go? I can go to vertex number 4. So I will, this time I will go to vertex number 4. Okay, so join the edge between those two. So 3 to 4 I can go. Okay, then from 4 where else I can go? I can go to 5 or a 1, but 5 is already covered. I cannot go to 5. Where else I can go? I can go to 1 over here. So from 4 to 1 I can reach. So when I reach to 1, what it gives me? It gives me a solution, that is another solution of this particular graph. That is, if I go in the direction 1, 2, 5, 3, 4 and 1, it is satisfying all the bonding functions and the definition of the Hamilton cycle, wherein I started from the one of the vertex and I could visit all the remaining vertices exactly once in the traversal, and I could come back to the first vertex, that is the starting vertex. So this is one of the solution. So like this way we can try to find out the solution to the given problem by using the backtracking method. So is this particular concept understood, students? Any doubts? You may need to unmute yourself and answer, because I'm not able to hear anybody's voice. It's muted. So are there any doubts over here? Okay. So let us try to see the another example for the Hamiltonian cycle. Okay. The second example is this one. Okay. Now in this particular graph, how many vertices are there? There are total 8 vertices, and we need to find out the solution for this one. Okay. So for this particular example, what I will do, I will just take the notes and then I will try to show you how the state space tree is drawn over there. Okay. Okay, before going to that, we may just see the definition also. Okay, Hamiltonian cycle. Let GVE be a connected graph with n vertices. A Hamiltonian cycle is a round trip path along n edges of the G that visits every vertex once and returns to the starting position. In other words, if a Hamiltonian cycle begins at some vertex V1, which belongs to the graph G, and vertices of G are visited in order V1, V2, V3 dot 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 until Vn plus 1, then all the vertices are distinct except V1 and Vn plus 1, because V1 is the starting and Vn plus 1 again it will be a starting vertex. So we start from one of the vertex and we will come back to the same vertex by making a round trip. That exactly we need to visit all other vertices once except the first vertex, because we are returning back to the first vertex. Okay, the same example is shown over here. It is been drawn. So in this particular diagram, wherever you see two lines, okay, that is two edges, from 1 to 2 there are two, from 2 to 5 there are two, that indicates that it is one of the solution. And whenever there is a dead end, when we are killing the continuation of drawing the subtrees, there we are marking it as a dashed lines. So here in this one, this is a dead end and these two are again a dead end, and the other two are the solutions. Okay, so let us see the another example here. The other example is here: 1, 2, 3, 4, 5, 6, 7, 8, and you may see here from 8 to 2 it is connected. Okay, and also 1, 2, 3, excuse me, sorry, from 1 to 3 also is connected. Now here we need to find out the set of solutions which gives us the Hamiltonian cycles over here. Okay, can anyone quickly tell me what could be the solutions over here just by looking at the diagram? Anyone? Would you try to answer? Give the solutions over here. If we travel in which particular order, we would be getting a Hamiltonian cycles here. 8 to 2 is also connected. For a better diagram, I can show this one. Can you tell me? I think 3 to 6 is also there. Yes, 3 to 6 is also connected. Anyone? Ajay? Indrabhushan? Are you on the call? Okay. Now suppose this is 2, 3, right? Okay. This is the example. 1 to 3 is there, not 1 to 2. Okay. Anyone will try to give the answer? Fine. See, if we start from vertex 1, say if you say 1 to 2, if we travel, let us try to see here without drawing the state space tree. Say from 1 you go to 2, 3, from 3 to say 5, this is 6, from 5 to 6, 6, what is this, 1 2 3, sorry, there is a mistake while typing here. 1 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, and from 8, 8 is connected to what? 2. So if I want to go back to 2, is it allowed? No, it is not allowed, because in this previous list 2 I have already covered. I cannot visit this 2 once again, so it is not accepted. So there is a dead end at the vertex 8. I cannot proceed further. Okay, right. Then what are the other methods I can travel to find out the Hamiltonian cycle? Okay, say let us say from 1 I can go back to 2, I can go to 2, from 2, since 2 is also connected to 8, so I can go to 8 here, 2 to 8, from 8 to 7, 7 to 6, 6 to 5, 5 to 4, okay, 4 to 3, 3 to, I can go back and reach the starting vertex, that is 1. See, all these I have visited exactly once and I have covered all the vertices. And from 3, I can go back to the starting vertex 1. So this will give me one of the solution. This is one of the Hamiltonian cycle. What could be the, if there exists one solution, then there must exist the mirror image of that one. Mirror image means from 1, I have to go in this, I have to read in this particular reverse direction. So from 1, I can go to 3, right? 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8, 8 to 2, and 2 to 1. 2 to 1. So this is also another solution. Okay, so these solutions we should get by drawing the state space tree. Okay, in the example over here we may see that. Okay, let us see how this particular diagram is drawn. Say we have started from 1, from 1 to 2 we could able to draw. One second, let me put it in a better angle so that the problem as well as the solution are seen. Okay, fine. So I start from the vertex 1, from 1 to 2 I will go. Yes, 1 to 2 I traveled. Since from 2, 8 I will travel, that is 2 to 8, right? From 8 to 7, so 8 to 7, so 7 to 1. So this is something mistake here, it is not 1, there doesn't exist a 1. So 7 to 6 I can go. From 6 to 2 possibilities, that is I can go to 3 and I can go to 5. From 6 to 3 I can go, but if I go to 3 I would be losing the other 2 vertices, so that is an dead end. So I can, where else I can go? I can come back to previous vertex 6, and 6 to 5 I can go. From 5 I can go to 4. Okay, from 4 I can reach 3. From 3 there are two possibilities. I can either go to 2 or I can go to 1. If I go to 2, what happens? Which becomes an duplicate, so it is a dead end. So I will come back to 3, and from 3 I can reach to 1. So I started from 1, and in this particular where two lines are drawn in that particular path, okay, I could able to reach or visit other vertices exactly once, and I could come back to the starting vertex. So this particular path gives me a one of the Hamiltonian cycle. So like this way, if you try to draw the state space tree, you would be able to get one more, which is a mirror image of this particular path. So second solution. So for the point of examination, you would be getting a suppose for 5 marks, if you get a question on the Hamiltonian cycle, the question would be what? Define Hamiltonian cycle, or what is Hamiltonian cycle? Okay, and they may give one particular graph and ask you to write the or represent the state space tree and find the set of solutions. Or the other question could be write a note on Hamiltonian cycles with example. So over there you need to write the definition, and you have to take one of the example and you have to solve. In that case, probably the previous example would do. Okay, if we can take this particular example and draw the state space tree with the solutions, that will give you the full marks. Any questions here, students, as of now? Okay, fine. So after this one, in your notes you have something called as graph coloring. Next concept is graph coloring. Okay, this particular concept is not there in your current syllabus. The graph coloring is not there in your syllabus, so we will not study this one. Okay, you also better not to go into this particular concept. Okay, then the next concept is sum of subsets. Okay, this concept is there as per your syllabus, so we will try to study sum of subsets. Okay, so let us study what is sum of subset. Suppose we are given n distinct positive integers. Okay, the integers here are represented as weights, and we desire to find all the combinations of these integers whose sum is m. This is called as sum of subsets. Okay, now let us take an example and try to understand what this particular sum of subset is. Say that, let me have it over here. Say that what it says, we are given n distinct positive integers, that is weights. Okay, say 1, 2, 4, say 5, 1 plus 4, 6, 5, 10. Okay, 1, 2, 4, 5 and 6. This is given set of positive integers. Okay, and these are nothing but the weights. In other terms, these are weights. What is the other part of the definition? We desire to find all the combination of these integers whose sum is m. Means if I say m is equals to say 10, means I need to figure out, I need to take the integers from here whose sum would be equals to m. Okay, if you try to remember something we have studied earlier, knapsack problem. Okay, so similar to that one, not exactly the same one, it is just similar to that one. Say that these are the different weights and this is the sack. I need to choose the weights from here. Okay, so here I need to choose the fully weights, not a fractional weights. I have to choose the fully weights, and I should exactly meet the sack. That is, I should exactly able to fill the given sack over here. I need to find out the what are the subset of this one. So if suppose if what are the possible solutions here? Say 1, if I choose 1 and 5 and 4, that is 1, 4, 5. So if I have one set 1, 4 and 5. If I add all these, what I will get? I will get as a 10, which is exactly equal to. What are the other solutions I can have here? Suppose if I have 4 and 6, then again I will get a 10. Okay, these are the two solutions, means these are the two subsets of a given set of positive integers. And if I add all these subsets, suppose if I add all these subsets, then I would be getting the sum as m. And here also, if I add all these subset values, I would be getting the sum which is equals to m. So the bounding function here is m value. Okay, so again, this particular problem can be solved using backtracking approach. Okay, how this particular backtracking approach is used over here? As I said earlier, we need to either choose that particular weight, or we may not choose it. We may choose or we may skip it here. Okay, so backtracking tree for this one, how it is drawn is that, let us try to see here. Okay, suppose I start from one of the vertex. As of now, this particular vertex, what I say that initially in this particular example, the vertex will indicate the sum of the subsets. Okay, at the beginning, say the m is 0, indicating that I have not chosen any of the vertices over here. I have not chosen any of the integer values here. Okay, so initially it will be a 0, that is the sack is empty. So what I can do here, I can choose the first weight. Okay, means I can have two possibilities over here. I can have two possibilities. What are those two possibilities? I can insert or I can add weight 1 into my sack, or I cannot add. I will or I will not. That's okay. So with respect to that, the sack I will try to draw the state space tree over here. Okay, so first initially I will draw the edge between these two. Let me draw the edge between these two. So 1 2, sorry, from this vertex to this vertex I will draw. Okay, then other is from here to here I will draw. So here what I will indicate is that if I go in this direction, what I say that this is if I involve, that is with vertex 1 or with weight 1. With weight 1 means I would be adding weight 1 into my sack. So my sack will contain weight 1. In simple terms, you try to understand this particular problem as that these are all in terms of kgs and total capacity is 10 kg. So that 10 kg sack I'm trying to fill in, okay, with 1 kg of certain content. So I added 1 kg into that one. So I have two possibilities. I can add that into my sack or I may not add it. That is with 1 kg, other would be what? Without 1. With 1 and without 1. So without 1 in the sense what? If I don't add 1 into the sack, what sack will contain? Sack will contain nothing as of now. It will be again 0 kgs. Okay, like this way I will try to draw the state space tree over here. Okay, this is important. Try to understand this once again. So initially the starting node, we treat it to be the sack as the example. Okay, which will contain nothing. That nothing is indicated as 0 value. So given n integers are these 1 2 4 5 6. What I will do, I will start from 1. What I can do is that I can add this 1 into my sack or I may skip it. That is with 1 and without 1. With 1 in the sense I am adding this particular 1 weight into the sack. So when I add 1 kg into the sack, so from 0 to it will become 1. Okay, without means again it is as the same as the previous value, that is 0 itself. Okay, now if I choose this particular tree in this direction, from 1 what I can do, I can add 2 also. I may not add 2 also. Again, two possibilities are there. So again the same things are mentioned over here. Suppose I can have two possibilities like this. Okay, so this will be what? Let me draw the tree here. Join the edge 1 to this particular edge and another vertex 1 to this edge. Okay, Now again here is what? This particular edge is with 2 and this is without 2. With 2 means I will be adding 2 into 1. So that is it will become 3. Without means same as the previous one, it is 1. Okay, then again what I can do? I can do with this particular 3. I can keep on adding in this particular direction or I can go in this direction. Always left side is something with and right side is without. So from, one second, this is not 3, right? Okay, this is 3. The sum of 1 plus 2 is 3. Okay, then again next is what? From 3, this particular node I can have 2 possibilities, with or without 4. So with or without 4 means what? So I will join this particular diagram, this edge, and the other edge is this way. This side is with 4 and this is without 4. So with 4 means 3 plus 4, that is 7. Without 4 means same as the previous value, that is 3. It is 3 itself. Then again I can continue in this direction. So from 7, what I can do? I can add the next value 5. Now suppose if I add here, okay, let me try to add that side. Say this is 7 to over here. So this time what I'm including? I'm including the 5 over here. So with 5. So what happens here? With 5 means 7 plus 5, which is 12 over here. But what is the solution? I should get the solution exactly where m is equals to 10. But what weight I am getting here? 12, which is not the given solution, because the sum should exactly become 10. But here it is more than 10. So this is this is not the solution. So there is a dead end over here. So I cannot go with this one. What is the other solution here? With 5 I have taken. So other could be without 5. Without 5 means it will be same as the previous value, that is 7 value over here. Okay. So if I draw the edge between this one, this is over here. So this is without 5. So when I go to without 5 as 7, after 5 what value I have? 6 I have. So again if I try to have 6 over here, what it will happen? 7 plus 6, which will again more than 10. Okay, so that is again not a valid solution. So I cannot proceed further, which will become a dead end. So what I should do? I should come back to 7. So after coming back to 7, I should come back to 3 over here. So from 3, without 3 way I have to go. So like this way, I can go with or without the weights and try to find out the solutions. Wherein, if I reach the dead end, and the dead end should have exactly 10 as the value. If I have the 10 value, then that particular depth first search path will give me one of the solution. Okay, it is little difficult to draw and explain all the steps on the sheet over here. So what I will do is that I will just show you the examples which are solved over here. Okay, so in this particular we have taken one of the example here, say 1, 2, 5 and 7. Okay, 1, 2, 5 and 7. And what the m value they have taken here? Have they given it? Yes, m value is 8. So we need, it is sometime they may represent it as a m or a d. Okay, so this is the subset, that is 1, 5, 2, 7, and the total sum should be 8. So we need to choose it. So here you may see what they have mentioned over here. Let me maximize little bit. Okay, sum initially it is 0, plus 1, minus 1 they have shown. Minus plus 1 means with weight 1, minus means without weight 1. Minus means do not subtract anything. Minus indicates without that particular weight. Plus indicates with that particular weight. Okay, so plus means we can add here this 0, we can add 1, but do not subtract 1 whenever there is a minus sign. That minus sign here indicates it is a without. So from 0 I can have with 1, without 1. With 1 means 0 plus 1 is 1. Without 1 means the same as the 0. So 0 is over here. So this 1 and 0 are populated. Now from this 1 I can do in multiple ways again. From 1, see again they have drawn it wrongly basically. From 1, what is the next value we have here? It is 5 actually. So it should be plus 5. Okay, this graph, this tree is drawn wrongly. Okay, we should always choose the values which are in the same sequence. After 1 there is a 5, I should take 5 here, so it will be plus 5, like that we should go. Okay, but I will just try to explain whatever they have drawn here. From 1 plus 2 means from 1 plus 2 it is 3. Minus 2 means without means I'm not considering the weight 2, so it will be same weight as the previous, that is 1 and 1 over here. Okay, then from 3, after this one again I can choose 5 or I may not choose 5. So that is plus 5, that is with 5, and minus 5. Minus 5 means without 5. Plus 5 means what will happen? 3 plus 5 is 8. Okay, then 3 minus 5 means same as the previous value, 3 over here. Then from 8, what is the next value? 7. But here if you see from 7, if you go with 7, 7 plus 8 is what? It is going to be 15. But our solution, what we require? 8. That means at this particular stage, we have reached our solution. This value is giving us the valid solution. That is, if we have this particular sequence, then that is one of the solution. Okay, like this, wherever you find the leaf node to be value 8, which will be giving us the solution, and wherever there is leaf node are not 8 or something different, it could be less or it could be more, then those are called as non-solutions. We have the dead end. So this is one of the dead end. Okay, and this grayed out, all these grayed outs are the dead ends. Okay, this is what sum of subsets. Sum of subsets as well as the Hamiltonian cycles are very simple concepts. Okay, if you just go through once again these notes and try to solve them, so you should be able to get the answer. There is one more example they have taken, 6, 8, 2, 14. Again here we should not consider in increasing order or any other order. Whatever is being given over there, the same way we should consider it. Probably I may solve these examples once again and then I will give it to you. This is not the correct method of solving the problems. Since initially it is given as a 6, I should choose 6 over here. 6, then 8. If 8 continue in the same order, 2, 14, like that's only we should do it. Okay,